In the year 1910, an English radiochemist by name Frederick Soddy discovered something very interesting. He was doing research on radioactive substances, and we know there are some elements like uranium, thorium, polonium that spontaneously emit some invisible particles called alpha and beta particles. And the interesting thing here is, after emitting these particles, atoms of an element change into atoms of an entirely different element. Say this element A is radioactive and it emits alpha particles. After emitting these particles, atoms of A become atoms of a different element B. Say B is also radioactive, but this emits beta particles. After emitting beta particles, atoms of B become atoms of another element C. Say C is also radioactive and it also emits beta particles. Again, after emitting beta particles, atoms of C become atoms of another element D. So, an alpha and two beta particles got emitted in this sequence, and atoms of A finally became atoms of D. Another interesting fact here is, if this is the position of the element A in the periodic table, then the element B that A got changed into after emitting an alpha particle is found two places to its left. So this will be the position of B. And the element C that B got changed into after emitting a beta particle is found one place to its right. So this will be the position of C. And again, after emitting a beta particle, C changes into D, so D will be found here. So A and D are in the same exact location in the periodic table. But see, in this process, an alpha and two beta particles got emitted. So some mass got kicked out of the atoms. So obviously, atoms of A and atoms of D do not have the same mass. They do not have the same atomic weights. Atoms of D are lighter than atoms of A. And according to John Dalton, atoms of the same element have same mass, atoms of different elements have different masses. So because A and D have different atomic weights, Soddy thought that they are two different elements. But when he took a mixture of A and D and tried to separate them using chemical methods, that is chemical reactions, he totally failed. He found that it is impossible to separate A and D by chemical methods. They have identical chemical properties, zero difference in their chemical properties. So he thought that A and D are two different elements that have the same position in the periodic table with identical chemical properties. Because they have the same position in the periodic table, he called them isotopes. Iso means same, topos means location. Two different elements found in the same exact location in the periodic table. And 2 years later, in the year 1912, the famous physicist J.J. Thomson discovered something related to this, but without using radioactive substances. Using his discharge tube experiments, the kind of experiments we studied in our lower grades, Thomson found that all the neon atoms found in nature do not have the same mass. The neon atoms found in nature have at least two different masses. So that means all neon atoms are not identical. And John Dalton was wrong. He said atoms of an element are all identical and have the same mass. But Thomson found that neon atoms found in nature could have different masses. So this means atoms of the same element need not have the same mass. They could have different masses. We understood it for the first time in 1912. Therefore, from this experiment and from his own studies, Soddy understood that actually A and D are not two different elements after all. They are atoms of the same element with different masses. Atoms of the same element could have different masses. Therefore, A and D are not two different elements as Soddy originally thought. They are atoms of the same element A with different masses. So that is what isotopes are. Isotopes are atoms of the same element with different masses. After that, we started discovering isotopes of many elements in nature. Hydrogen has 3 naturally occurring isotopes. Neon has 3. Oxygen has 3. Of course, there are some elements like sodium and gold that are monoisotopic. That is, each of them has only one naturally occurring isotope. Earlier, we thought all atoms of an element are identical, so there was only one atomic weight per element. But now we discovered isotopes. Atoms of an element may have different atomic weights. So now we have to deal with multiple atomic weights of the same element. The number of times an atom of a particular isotope is heavier than a hydrogen atom or whatever reference we took is called isotopic weight or the atomic weight of that isotope. So because oxygen has 3 naturally occurring isotopes, there are 3 isotopic weights of oxygen, 3 for neon, 3 for hydrogen. So this is going to cause some problem for us. Now we have to deal with multiple isotopic weights of the same element. So we have to find a solution to this problem if possible. We don't want to deal with multiple isotopic weights of an element. We need a single atomic weight per element. Let us see. You take a sample of any element from natural sources. It is always a mixture of all its naturally occurring isotopes. You will not find a pure sample of a single isotope anywhere in nature. And the share of each isotope is called its isotopic abundance. And all the isotopic abundances of an element put together is known as its isotopic composition. And the interesting thing is, the isotopic composition of an element is a constant everywhere in the world. It might change a little bit from one location to another location, but we can ignore that variation for our purposes. So you take a sample of oxygen from anywhere in this world, it will have all the 3 isotopes of oxygen in this proportion, more or less. Also, the isotopic composition of an element is same whether it is in the form of an element or in the form of a compound. Oxygen is present in air in elemental form, that is what we breathe. Oxygen is present in the form of carbon dioxide in air. It is present in the form of minerals in Earth's crust. It is present in the form of water in lakes, rivers, and oceans. It does not matter in what form it is present in. Its isotopic composition is same in all these forms. And the chemical properties of different isotopes of an element are identical, though they have different masses. That means chemical properties of different isotopes of a given element are independent of their masses or their atomic weights. Because of these reasons, we can ignore the fact that the element is actually a mixture of different naturally occurring isotopes and consider that it is made up of identical atoms to avoid dealing with multiple isotopic weights. This picture solves our problems. So, we imagine oxygen is composed of identical oxygen atoms, though it is actually a mixture of oxygen atoms with different atomic weights. So, in case of elements that have more than one naturally occurring isotopes, because it is difficult to deal with different isotopic weights of that element, we can imagine that the element is actually composed of identical atoms, though it is a mixture of atoms of different isotopes of that element with different masses. Let us say M1, M2, M3 are the atomic masses of different naturally occurring isotopes of an element, and A1, A2, A3 are their respective percentage abundances. That means in any natural sample of that element, per 100 atoms, there are A1 atoms with mass M1, A2 with mass M2, A3 with mass M3, say in AMU. Now I will imagine that I added up these 100 atoms into a big mass and then divided that into 100 identical atoms. It is these imaginary identical atoms that I assume that the element is composed of. And this imaginary atom is what is called the average atom. And the atomic mass of this imaginary average atom is what is called average atomic mass of that element, or simply the atomic mass of that element. What is the mass of this imaginary lump? This is created by adding up these atoms, right, in our imagination. A1 with mass M1, A2 with mass M2, A3 with mass M3. So the total mass of the lump would be A1 M1 plus A2 M2 plus A3 M3. Then we divided that into 100 identical atoms. So this is the expression for the average atomic mass, or simply atomic mass of an element, where A1, A2, A3 are the percentage abundances of different isotopes of an element. M1, M2, M3 are their atomic masses. And if you remove the unit AMU, it becomes average atomic weight, or simply atomic weight of that element. So we assume that the element is composed of identical atoms with this atomic weight, though it is actually a mixture of different isotopes of that element. By the way, do you remember what we call this kind of average? It's called weighted average, right? We did a similar example before with fruits. So average atomic weight, or simply atomic weight of an element, is the weighted average of isotopic weights of different isotopes of that element, calculated taking into account their percentage abundances. Don't say it is m1 plus m2 plus m3 over 3. This would be wrong. Atomic weight of an element is a weighted average. And we shall understand this average atom more clearly with the classic example of chlorine. We say the atomic weight of chlorine is approximately 35.5, but there is not a single chlorine atom out there in nature with this atomic weight. Then why do we say the atomic weight of chlorine is this? Because this is the weighted average of different isotopic weights of chlorine, taking into account their percentage abundances. Or simply put, this is the atomic weight a chlorine atom would have if all the chlorine atoms in this world are identical. It is the atomic weight of an imaginary chlorine atom, assuming that all the chlorine atoms in the world are identical. So we solved that problem by taking the weighted average of the isotopic weights of an element as the atomic weight of that element. But remember, we can use the atomic weight of an element only if we use that element in its natural form. For any reaction, if we use a purified sample of a particular isotope of an element, there we have to use the isotopic weight of that isotope, not the weighted average atomic weight of that element. Now, isotopes have created another problem for us. I mean, isotopes of oxygen. Oxygen has 3 naturally occurring isotopes with 3 slightly different masses. Remember, we started using 1/16th of the mass of an oxygen atom as the reference for atomic weights on the new oxygen scale. Earlier we thought all oxygen atoms are identical, but now we understand that there are 3 different types of oxygen atoms in nature with different masses. So when we say we took the mass of an oxygen atom as 16 AMU, mass of which oxygen atom? Let us see. Chemists determine atomic weights using chemical reactions. Such methods are known as chemical methods, wet methods, or Harvard methods. As we just discussed, a chemist imagines that oxygen gas is composed of these imaginary identical average oxygen atoms. Ultimately, as far as chemical reactions are concerned. So a chemist would say, I took the mass of this imaginary average oxygen atom as 16 AMU. But physicists do not use chemical reactions to determine atomic weights. They use mass spectrometers to determine atomic weights. A mass spectrometer can detect and separate various isotopes of an element. We shall discuss very briefly how mass spectrometers work towards the end of this discussion. But look at the isotopic composition of oxygen. Though oxygen has 3 isotopes, the abundances of these 2 isotopes are very low, and those early mass spectrometers were not powerful enough to detect these isotopes because their abundances are very low. So they could only see the most abundant isotope of oxygen in those mass spectrometers. So a physicist would say, I took the mass of the most abundant oxygen atom as 16 AMU. The oxygen atoms that I could see in my mass spectrometer. So obviously, this created a divide between physicists and chemists as far as these atomic weights are concerned. Physicists took the mass of this oxygen atom, the most abundant oxygen atom, as 16 AMU. Chemists took the mass of this imaginary average oxygen atom as 16 AMU. Obviously, these two atoms do not have the same mass. We can tell that from our understanding of averages. So, the size of the reference used by the chemists and the size of the reference used by the physicists are not the same. Atomic weight is a ratio between these two masses. If these two references do not have the same masses, then these ratios will not be same. That means atomic weights determined by chemists and atomic weights determined by physicists differed by a small amount. They are not the same. So, unintentionally, chemists and physicists ended up on two different atomic weight scales, and this created a problem for us. We don't want to deal with two different atomic weight scales. So, after using two separate atomic weight scales for many years, they both agreed to replace these two atomic weight scales with a single atomic weight scale. Then the question is, what should be used as the new reference? Okay, what should be taken as the new reference for atomic weights? There was one suggestion from the physicists, that is, pick a real atom, an atom of an isotope, as the reference. We cannot see these average imaginary atoms in our mass spectrometers. Therefore, pick a real atom as the reference, and it's fine even if our atomic weights change a little bit. And as usual, chemists said they cannot afford big changes to their atomic weights. The atomic weights on the new scale must be as close as possible to their existing atomic weights, because their atomic weights are used by many people. So these are the two requirements we must keep in mind in selecting a new reference. And by a stroke of sheer luck, we found one reference that satisfied both these requirements. Element carbon has 3 naturally occurring isotopes. Of these 3 isotopes, the lightest and the most abundant isotope is called C12 isotope. We shall understand the significance of this number 12 later. But this particular isotope of carbon satisfied both these conditions. Therefore, in the year 1961, a new atomic weight scale was started based on the mass of one atom of C12 isotope. And the mass of an atom of C12 isotope was taken as 12 units exactly. Because this new scale was started to unify or replace two separate atomic weight scales used by chemists and physicists, this unit is called Unified Atomic Mass Unit. Remember, earlier there were two different atomic mass units. One AMU used by chemists and one AMU used by the physicists. And this new unit unified these two separate AMUs. That is why it is unified atomic mass unit, and its symbol is small u. In honor of John Dalton, it is also called Dalton, and the symbol for Dalton is Da. And obviously, 1U is equal to 1/12 of the mass of one atom of C12 isotope, and this is the new reference for atomic weights. And this is the reference that we use even to the present day. As usual, the definition of atomic weight on this new scale is mass of one atom of the element over 1/12 of the mass of one atom of C12 isotope. Remember, many people incorrectly refer to this unified atomic mass unit as AMU, atomic mass unit. AMU was the unit on the previous oxygen scale. Actually, there were two different AMUs. On the new C12 scale, the name of the unit is Unified Atomic Mass Unit, and its symbol is U or Da, not AMU. But in many books, U and AMU are used synonymously. So keep that in mind. And just as they started this new atomic weight scale, they said there is another problem that needs to be fixed. They said they have a problem with the name atomic weight itself. See, whatever we are calling atomic weight is neither mass nor weight. It is not at all a physical quantity. It is a ratio between two masses, and it is a dimensionless number. It tells the relative mass of an atom relative to some reference. So they said it must be clearly reflected in its name, so they added the word relative to its name. Then it became relative atomic weight. Now there is another problem with this name. See, mass and weight are not the same. They are two different things. Mass is the amount of matter present in an object, and it is same for a given object anywhere in the universe. But weight is the force experienced by that mass when it is placed in a gravitational field, and it could change from one location to another location. Therefore, clearly mass and weight are two different things. What we have here is relative mass. Therefore, they replaced the word weight with mass. So they have come up with a new name for atomic weight, that is relative atomic mass. So relative atomic mass and atomic weight are one and the same. It is the ratio between these two masses, and it is a dimensionless number. Similarly, we can rename molecular weight to relative molecular mass, isotopic weight to relative isotopic mass, formula weight to relative formula mass, and ionic weight to relative ionic mass. See, in all these definitions, we have changed the reference. 1/12 of the mass of one atom of C12 isotope is the new reference. Now we are ready to conduct some chemical reactions.